Hi, my name is Anna, and we are going to be talking about this problem on the board. So we are given a situation where there is a closed capillary tube. So the things we are going to want to consider is that it's a closed system. Both species, A and B, are ideal gases. The molecular weight are going to be described as Ma and Nb. And let's just say that the molecular weight for B is going to be greater than the molecular weight of A. And then we're also going to say that the temperature and pressure are the same and constant. So species A and B are in this capillary tube, and there is a divider down the middle, so they're equal volumes for both sides. And then this is going to be the positive z direction. Now the goal of this problem is to find an expression of the molar diffusive flux and the mass diffusive flux in terms of molecular weight, gas A, and the mass fraction. Okay, so what is flux? Well, flux means that there's a net flow, but in general terms, flux is a net flow all over an area. So we're given two equations. The molar flux of A is going to equal the molar concentration of A, I'm putting this in terms of species A, and the molar average velocity of A. We are also given another one. The molar flux is the molar diffusive flux of A plus the molar concentration of A times the net molar average velocity. So why does this equation make sense? Well, let's think about it. So there is molar concentration of A times an area times the distance all over time. Well, the area and distance represents a volume, the molar concentration moving through a volume over a time. That's net flow. We put that all over an area. Well, the areas are going to cancel, and that leaves you with the molar concentration times a distance over a time. So then that just gives you molar concentration times the molar average velocity of A. All right, so let's look over here. Once you remove the divider, the molar concentration, the molar flux of A is going to want to move to the positive z direction, and the molar flux of B is going to want to move in the negative z direction. Why is that? Well, the concentration gradient is the greatest here. This is not uniform. There's A on this side and B on this side. So what they want to do is they want to mix and become uniformly distributed. So that's why there's the greatest concentration gradient here. It goes from pure A to no A, and the same for B. Pure B to no B. So over here, the net molar flux is going to be 0. Now, why is that? Well, no molar flux of A or B is going to be going outside of the system, and none is going to be coming in. Why? Well, because this is a closed system. So then that actually has to mean that anywhere in here, the net molar flux should also be 0. Now, why is that? Well, we can look at the ideal gas law. So we all know this general equation. PV equals N RT. Now, let's put this in a different form. The amount of moles over volume equals P over RT. Now, earlier we said that we wanted the pressure and temperature to be the same and constant. Well, then that also means that the amount of moles for a specified volume also needs to be the same and constant. So let's look at this. The net flow of moles in needs to be the same as out. So that means here it should also be N equals 0, the net molar flux, because there's no accumulation inside this volume. There should be no accumulation. Okay, so how do we get from moles to mass? Well, to get to moles to mass, you just do moles times the molecular weight to equal mass. So in terms of molar flux, you can just do the molar flux of A times the molecular weight of A to equal the mass flux of A. Now, does this mean that the mass flux of A is going to equal 0? No. That doesn't mean that the mass flux of A is going to equal 0. And here's why. We said that hypothetically, that the molecular weight of B is going to be greater than A. Well, for every B that moves to the left, it's going to bring mass with it. It's going to bring more mass than 1 mole of A moving to the right. So that means that the net mass flux is not going to be, it's going to be the net, not for A. This is the net, not A. The net mass flux of the system is not going to be 0, because for every B moving to the negative Z direction, it's going to bring more mass than a mole of A moving in the positive Z direction. Okay, so let's talk about molar diffusive flux. The summation of the molar diffusive flux for the component I is going to equal 0. We can explain this by using the equation also given, that the summation of, let me write this out first. The summation of the molar concentration times the molar average velocity minus the molar concentration of I times the net molar average velocity. Well, we can rewrite this expression in another form. Let's just erase this real quick. So we get that the summation of the molar concentration component I multiplied by the molar average velocity, the net molar average velocity. That's the same thing as this. But then look, we also might subtract it from the same thing. This is just the same thing. So that is how we get 0. Okay, so now I'm going to erase the whiteboard, and then we're going to talk about the molar diffusive flux and the mass diffusive flux and find one expression so we can achieve this goal. Okay, so now we're back. Let's talk about, I also added that the molar diffusive flux of A plus the molar diffusive flux of B is going to equal 0. And then I also put that the net molar flux is going to equal 0. So then that also means that I can rewrite the molar diffusive flux of A plus a molar diffusive flux of B to equal the net molar flux, which equals 0, to be the molar diffusive flux of A equals the negative molar diffusive flux of B. All right, so let's talk about, also, the partial pressure of the system. We said that it's going to be the same. So it's going to be P here and P here, just to symbolize that they're the same. But then when we remove the divider, we can say that the partial pressures of A and B are going to be P over 2. So the same can be written for partial pressure of B to be equal to P over 2. Just wanted to make sure I added that. Okay, so let's talk about molar diffusive flux and putting the mass diffusive flux in terms of molecular weight, gas A, and the mass fraction. Okay, so we're given an equation of, sorry, that's my cat. One moment. We're gonna cut and I'm gonna excuse the cat. Say bye to everyone. Okay, we're back. So let's talk about this. Let's look at the general equation for this. So the molar flux, the net molar flux is going to equal the concentration times the net molar average velocity. So if the molar flux, the net molar flux of the system is going to be equal to 0, well, then that's going to have to mean that the net molar average velocity is going to also have to equal 0. Because there is concentration in this situation. There's stuff in here. So that means that it can't be 0. So that's going to be important later. Let's also rework this. So let's see. Let's look at the equation where the molar diffusive flux of A is going to equal, no, sorry, I messed that up. Let's look at the equation where the molar flux of A is going to equal the molar diffusive flux of A plus the molar concentration of A times the net molar average velocity. So let's look at that. So if the net molar average velocity is going to be 0, well, that gets rid of this. That simplifies things. So then let's also look at turning this into another equation. Well, if the molar flux of A equals the molar diffusive flux of A, we can rewrite it using this equation. We can say that the molar diffusive flux of A, of component A, equals the molar concentration of A times the molar average velocity of component A. So let's rewrite that also, so that it is the molar average velocity of A equals the molar diffusive flux of A all over the molar concentration. Okay, so let's talk about the molar diffusive flux and the mass diffusive flux so we can reach our goal expression. Okay, so mass diffusive flux, and we're going to put it in terms of A, is going to equal the mass fraction of A times the velocity for component A minus the net mass average velocity. Okay, so what can we do from here? Well, we already reworked this so that the velocity for component A is going to equal the molar diffusive flux of A over the molar concentration of A. And the same thing can be done for B. And we'll use that later. Okay, what else? So what's velocity? Well, velocity is, we can put it in terms of molar mass concentrations and the individual components of average velocities. So let's do that. So mass concentration of A times the velocity, mass average velocity component A, plus the mass concentration of B times the velocity, the average velocity for component B, all over density for the mixture. Okay, so let's plug that in. Okay, so now we can distribute this, and I'm also going to plug in the average velocity for component A into this equation again for right here. So if we distribute the mass concentration to this first part of the expression, then we're going to get the density, the mass concentration of A over the molar concentration of A. Now, what is that? So mass concentration, that's kilograms over meters cubed. Molar concentration is just moles over meters cubed. Those meters cubed are going to cancel, and then you're going to have kilograms per mole. And what is that? Molecular weight. And we have those variables. So we can just plug in an MA for molecular weight of A times the diffusive flux of A, subtracted by, and we're going to distribute this out, the mass concentration of A times the mass concentration of A times the molar diffusive flux of A all over the molar concentration of A, and then do the same thing for species B. So then what are we left with again? We can simplify this more. So we see that there's a density over concentration again. So we're going to simplify it the same way using molecular weight. So the last way to simplify this to get our desired expression, we're just going to turn this into mass fraction because this is a mass concentration over the density for the entire mixture. So then we're left with the final expression of the mass diffusive flux of A equals the molecular weight of A times the molar diffusive flux of A minus the mass fraction of A times the molecular weight of A times the molar diffusive flux of A plus the molecular weight of B times the molar diffusive flux of B. And then that's our final equation. Thanks for watching.